Hi there, this is Nuclear Physics Lesson 4, and this is Radioactive Decay Part 1. So rate of decay and activity, so pretty straightforward. The rate of decay, I'm going to write dN by dt, which is the rate of which the nuclei are decaying, is directly proportional to the number of nuclei present within the sample. Which makes sense because, the more nuclear material you have, the more decay you're going to have at any one time, so the rate of decay would indeed be higher. We could also put a negative in there to show that the rate of decay will decrease over time. However, what I'm going to do is to write dN by dt, get rid of the proportional sign and get a constant of proportionality in there, and write minus lambda n. Now lambda is the decay constant, or the disintegrations per second. There's a negative because it's decreasing the total amount of nuclear material. And instead of dN by dt, the rate of decay, we could also call that the activity. So an equation is the activity is equal to minus lambda times n. And the negative's in there just to show that the amount will be decreasing over time. So the activity is typically measured in becquerel, or the count rate per second. N is just a number, the number of atoms present, and the decay constant, if it's becquerel for activity, would be seconds to the minus 1. Or you could say the disintegrations per second. Make sure that's down, the equation, and then let's utilize it. So it's going to start off more straightforward and then get more difficult. So let's pause and have a go. Calculate the number of nuclei present if a mass of radioactive material has an activity of 2 times 10 to the 6 becquerel and a decay constant of 2.5 times 10 to the minus 9 per second. So its activity is lambda n. You don't need to use the negative. So activity is lambda n. So just put the numbers in. So activity 2 times 10 to the 6 equals decay constant 2.5 to the minus 9 times n. And then obviously divide, so 2 times 10 to the 6 divided by 2.5 to the minus 9 gives a number of 8 times 10 to the 14. 8 times 10 to the power of 14 atoms. Should be straightforward, that one. Let's move on, something a bit more difficult. Let's do a recap first. I'm going to recap Avogadro number. Remember, Avogadro number is the amount of atoms present in 12 grams of carbon-12. So let's say we had carbon-12. So in 12 grams of carbon-12, there are Avogadro number atoms. So there's 6.02 times 10 to the power of 23 atoms. So say we had helium-4. In 4 grams of helium-4, there would be 6.02 times 10 to the 23 atoms. Uranium-235. In 235 grams of uranium-235, there would be 6.02 times 10 to the 23 atoms. So this is Avogadro's number, 6.02 times 10 to the 23. And we can use that to find the mass of an individual atom. So I'm just going to give an example of that. So let's use carbon-12. So what you do is the mass, so carbon-12 would have a mass of 12 grams, 12 times 10 to the minus 3, divided by Avogadro number. So 12 times 10 to the minus 3 divided by 6.02 times 10 to the 23 would give the mass of a single carbon-12 atom, which is 1.99 times 10 to the minus 26 kilos. Let's do one more. Let's do helium-4. So helium-4. So that would just be 4 grams divided by Avogadro's number. So 4 times 10 to the minus 3 divided by Avogadro's number. I'm just going to write Na. That will give us 6.64 times 10 to the power minus 27 kilograms per atom of helium-4. So hopefully that recap's helped. Let's move on. So once I've got this question, try and figure this out, and then I'll take you through the answer. So Plutonium-238 has a decay constant of 2.51 times 10 to the minus 10 disintegrations per second. Calculate the activity of 50 milligrams of Plutonium-238. So we need to use the activity is lambda n. And what we can see is that we have the decay constant and just need to find the number of atoms that will be present within the sample. So to do that, we can find the mass of a single Plutonium-238 atom simply by doing, so it's Plutonium-238, so it'll be 238 grams, so 238 grams, or 238 times 10 to the minus 3 kilos, and divide that by Avogadro's number, which is 6.02 times 10 to the power 23. And that gives us a mass of 3.953 times 10 to the minus 25 kilos. Now, I'm writing 4 significant figures. You should, because these are intermediate calculations, it's probably best practice just to use the full number in the calculator. So your answer might be slightly different to mine, but don't worry. So that's the mass of a single atom. And we've got 50 milligrams of Plutonium-238. So what we need to do is 50 milligrams, which is 50 millis to the power minus 3, but then grams is also to the minus 3. So 50 milligrams is times 10 to the minus 6 kilos. A lot of people make a mistake there. If you've done that, don't worry about it. Just try not to do it in an exam. So divide that by 3.953 times 10 to the minus 25. So that gives us the number of atoms, which is 1.265, or thereabouts, 1.265 times 10 to the power of 20. Your answer might be slightly different because you're using the full numbers. Then we can just do activity is lambda n. So lambda is given at the top, so it's 2.51 times 10 to the minus 10 multiplied by the number of atoms, the 1.265 times 10 to the power 20, which gives an activity of 3.2 to the power of 10. So it's 3.2 times 10 to the power of 10 becquerel BQ. So hopefully that went okay. If you got that, really well done. If the milligrams didn't catch you out, even better. So let's move on to the next one. So Krypton-87 has a decay constant. Well, if you want to pause and have a go, please do, then I'll start. Krypton-87 has a decay constant of 8.99 times 10 to the minus 3 disintegrations per minute. So we need to deal with that. What we need to do is calculate the activity of 20 micrograms of Krypton-87. So let's deal with the decay constant first. Obviously, if that's per minute, we need to divide that by 60 to get it into seconds. So let's just divide that by 60. So that gives a decay constant that is equal to 1.482 times 10 to the power minus 4 disintegrations per second, to the power minus 4. Then we need to use activity is lambda n. So we've got lambda now, we need to find the number of atoms. So let's do that. So let's find the mass of a single krypton atom. So that'll be 87 grams, Krypton-87. So 87 grams times 10 to the minus 3 divided by Avogadro's number. So 6.02 times 10 to the power 23. And that gives us the mass of a single atom, which is 1.445 times 10 to the power minus 25 kilograms. Then we've got 20 micrograms to deal with. So again, you have to be careful. So it's 20 micrograms divided by the mass of an individual Krypton-87 atom. So 20 micrograms is 20 micros to the minus 6 and then grams is to the minus 3. So we've actually got 20 times 10 to the minus 9 kilos divided by that number that we just got, the 1.445 times 10 to the minus 25. That will give us the number of atoms present within the sample, which is 1.384 times 10 to the power 17 atoms. Then we can simply use activity as lambda n. So we're to multiply the lambda and the n together. So activity is equal to, so we've got the 1.482 times 10 to the minus 4 multiplied by the number of atoms, 1.384 times 10 to the 17. If you end up with a slightly different answer, don't worry, it's probably just a round-up error. So the activity will be equal to 2.1 times 10 to the 13. 2.1 times 10 to the power 13 becquerel. 2.1. Hope that one went okay. Right, let's do one more. Again, slightly different to this one. If you want to redo any of these questions, just watch the video again and redo them. So I'm going to pause and have a go at this one. So Strontium 90, SR90, has a decay constant of 0.024 disintegrations per year. Calculate the activity of 1 gram of Strontium 90. So, let's deal with the decay constant first. So we've done this before, but this time it's given in years. So we need to divide by the number of seconds in a year. So you'd have to do 0.024 divided by. So the number of seconds in a day is 60 times 60 times 24, which is 86,400. So 86,400 seconds. Multiplied by 365 days in a year. You could, if you put 365 in a quarter, that's completely fine. It won't change the answer too much anyway, but it gives you a decay constant of 7.61 times 10 to the minus 10 times 10 to the minus 10 disintegrations per second. Just like this. Then we need to find the mass of a single Strontium 90 atom and then figure out the amount of atoms in 1 gram. So it's Strontium 90, so it's 90 grams, so 90 times 10 to the minus 3, divided by Avogadro's number, 6.02 times 10 to the 23. This should be coming pretty automatic on your behalf by now. You've done this a few times. So 1.495, sorry, times 10 to the minus 25 kilos per atom. And then we need to do the 1 gram divided by that. So 1 gram is 1 times 10 to the minus 3 divided by the 1.495 times 10 to the minus 25, which gives us a number of atoms of 6.689 times 10 to the power 21. Then its activity is lambda n, so you just need to multiply the decay constant by the number of atoms. And if you multiply them together, you should get an activity of 7.61. Now I'm lying, an activity of 5.1 times 10 to the power 12 becquerel. Hopefully that went okay. And that makes sense now. So these can come up in, just about any exam. Well, obviously it's got to be an exam with nuclear physics in it, but any exam board, they like these ones. So be mindful of that and make sure you can do them. And thanks for watching, and I'll speak to you later. Cheers.